It was the year 2017 when astronomers spotted a bright star hurtling out of the Milky Way. It was moving incredibly fast at a speed of 2 million miles per hour. That's almost 4 times as fast as the Sun orbits around the center of our home Milky Way galaxy. It takes our star more than 225 million years to complete one journey. Anyway, back to our star, the Wanderer. The main issue with it was that it was moving against the direction in which most stars travel around the center of our galaxy. Even more bizarre, it consisted of totally different star stuff. Astronomers managed to identify its composition. The star was made up of heavy metallic atoms. At the same time, most of the other stars consist of way lighter elements. The wandering star got the name LP-40-365. It was moving so fast that it literally dashed out of our galaxy. This made scientists believe that the space traveler was pushed out of its place by some kind of cosmic disaster, like a supernova. A supernova is the largest explosion that can take place in space, an explosion of a star. It happens after irreversible changes start in the core of a star. Supernovas can occur in 2 ways, in binary star systems and when there's a single star. Binary stars are 2 stars orbiting around the same center. At some moment, one of the stars, a very dense white dwarf, starts stealing matter from its companion. After some time, this thief accumulates too much matter, which causes it to explode into a supernova. Or it can be a single star nearing the end of its life. It's running out of its fuel. More and more mass is flowing into the core of the star. In the end, the core becomes so heavy that it fails to withstand its own gravity. After the core collapses, a tremendous amount of energy is released in a supernova. But astronomers still can't figure out how a supernova could send LP-40-365 flying. There are more questions than answers. Was it a companion star that got flung out by a shockwave created by a supernova? Or was it a piece of the exploded star? A new study based on the collected data has shown that the star, which is a white dwarf, keeps slowly rotating around its axis. Astronomers are almost sure it means LP-40-365 is indeed just a chunk of space debris, and not a full-fledged star. This wandering piece somehow managed to survive one of the fiercest space events. But after making such a conclusion, scientists realize something amazing. LP-40-365's unusual features could appear after the star witnessed a supernova. Even though this event happened lightning fast, the entire makeup of the star got changed. Most stars consist mainly of helium and hydrogen, but LP-40-365 is different. It contains such heavy elements as magnesium, oxygen, and neon. It must have been the supernova that added these atoms to the star's composition. By the way, astronomers consider all elements that are heavier than helium to be metals. This means that after witnessing the supernova, LP-40-365 became metallic. Right now, the star doesn't have its own planets, but NASA's Transiting Exoplanet Survey satellite, which is on the lookout for distant planets passing in front of their host stars and dimming them, has noticed a curious thing. LP-40-365 brightens and then dims again every 8.9 hours. It might mean that the star pulsates, but usually stellar pulsations are much less regular. A more plausible explanation is that the star's surface is uneven, and as it spins, sunspots are brought into and out of view. And it's great news, because after astronomers figure out how fast the star rotates, they can understand what happened to it around 5 million years ago during the supernova. Bright blue exoplanet HD 189733b looks peaceful and eerily familiar. Doesn't it resemble Earth? But this appearance conceals the planet's terrifying nature. There, the winds blow at 5,400 miles per hour. It's 7 times the speed of sound. But that's not the worst. It rains glass, sideways, in this scorching hot world. Neutron stars are ultra-dense collapsed cores of giant stars. They emit X-rays or radio waves. But in 2018, astronomers discovered a weird stream of infrared light. It seemed to be coming from a neutron star 800 light-years away from our planet. The most plausible theory is that this signal was probably produced by a disk of dust surrounding the star, but there isn't enough evidence to confirm this idea. Mercury is the fastest planet in the solar system. It zips around the Sun at a breakneck speed of more than 100,000 miles per hour. That's around 40,000 miles per hour faster than our home planet. It's one of the reasons why a year on Mercury equals 88 days on Earth. Mercury is the planet that orbits the closest to the Sun. That's why if you were standing on its surface at its closest approach to our star, the Sun would look more than 3 times as large as it does on Earth. The Black Widow pulsar is a rotating neutron star that is munching on its partner, which is a lightweight brown dwarf star. The more material the pulsar consumes, the more slowly it spins. The energy the neutron star is losing in the process causes the companion star to dwindle. There's a stellar nursery in the constellation Centaurus, and even though this place is called a nursery, it's anything but peaceful or safe. It's made up of hydrogen and newborn stars and is located in a nebula around 6,500 light-years away from Earth. A nebula is a giant cloud of gas and dust floating in space. The intense energy baby stars emit makes hydrogen clouds glow ominous red. This energy is so powerful, it's eating away dark clouds of dust. Astronomers can see them disappear like lumps of butter on a hot frying pan. Faraway Neptune-sized exoplanet Gliese 436b is a paradox. It's made of scorching hot ice, and this ice is burning. The planet completes one full orbit around the red dwarf Gliese 436 in just 2 days. It means the exoplanet travels very close to its parent star. That might be the reason why the planet's temperatures rarely drop below 800 degrees Fahrenheit. But the strangest thing? The planet hosts huge volumes of water ice known as Ice X. And this ice remains solid despite such incredibly high temperatures. Jupiter is the largest planet in the solar system. It's 318 times as massive as Earth. It's also 2.5 times as massive as all other planets of the solar system combined. But here's a paradox. If this gas giant got even more massive, it'd actually become smaller. The added mass would make the planet denser, and this would cause it to start pulling in on itself. Astronomers claim that Jupiter can eventually end up being 4 times as massive as it is now. But at the same time, its size won't change. DGSAT-1 galaxy is as big as the Milky Way, but it's nearly invisible because its stars are spread out incredibly thin. But what makes the galaxy so unique is that it's sitting all alone, unlike other galaxies of this kind. Those are usually found in clusters. It can mean that DGSAT-1 was formed in a different era, probably a mere 1 billion years after the Big Bang. If it's true, the galaxy is a real living fossil. Saturn's moon, Hyperion, is one of the most bizarre-looking moons in the solar system. But the appearance isn't the strangest thing about this space body. The pumice stone-like rock is pockmarked with countless craters, and it's also charged with static electricity, which is flowing out into space. About 4,000 light-years away from Earth, there's a planet that seems to be one enormous diamond. The planet is denser than any other discovered so far and consists mostly of carbon. It's so dense that astronomers think this carbon might be crystalline. It means that at least some part of the planet is diamond. Ceres is the most massive space body in the asteroid belt between Jupiter and Mars. It totals almost a third of the entire mass of the whole belt. But at the same time, Ceres is the tiniest of the dwarf planets out there. It's also the only dwarf planet that dwells in the asteroid belt, and also the only one that is located in the inner solar system. Astronomers sometimes call Jupiter a failed star. The gas giant indeed contains a lot of helium and hydrogen. But its mass isn't enough to start a fusion reaction in its core. And that's exactly how stars produce energy. They fuse the atoms of hydrogen together under extreme pressure and heat and create helium. In the process, they also release light and heat. Jupiter could start a nuclear reaction and become a star only if it was 70 times its current mass. Space is completely, eerily silent, That's because in the vacuum of space, there's no atmosphere, and the sound waves need some medium to travel through. That's why worlds with atmospheres like Earth are full of noise. Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Even so, just one minuscule thing would have enough mass of 1,000 sedans. One theory claims that tons of micro-black holes could be created right after the Big Bang. Some scientists even go so far as to say that a couple of mini black holes pass through our planet every day. Every hour, the sun sends more energy to Earth than our planet uses in a year. Even though people are now using much more solar energy than a decade ago, it's still a mere 0.7% of the world's annual electricity usage. There might be moons orbiting other moons, but astronomers haven't agreed on this theory yet. Planets orbit stars, moons orbit planets. But why can't there be moons, also known as submoons, moonettes, and moons? Researchers claim that moons could exist, but the host moon has to be massive enough and the moon small enough. There must also be a large distance between these moons and the host planet. Jupiter is the most massive planet in the solar system. This means its gravity is also the most intense. It's 2.5 times as great as what we have on our home planet. Once, the gas giant's gravity even tore apart a large comet called Comet Shoemaker-Levy 9. Then the planet eagerly swallowed the chunks of the former comet. If you were standing at the equator on Mars, the temperature at your feet would feel like that of a warm spring day, but your head would be literally freezing. Lost in space and drifting through galaxies, rogue planets were once flung away from their parent stars, but one of them, floating 200 light-years away from Earth, is different from the rest. It's a planet-sized object with a magnetic field 200 times stronger than that of Jupiter. This field is so powerful that it generates never-ending flashing auroras in the planet's atmosphere. Europa is one of Jupiter's largest moons, even though it's smaller than Earth's moon. But the cool thing about this satellite of the gas giant is that it's covered with ice. And some of this ice is smooth, which means you could skate there. And a 3-foot axle jump you can perform on our planet would take you 22 feet into the air. At the same time, the landing speed on Europa would be the same as it is on Earth. Haumea, a dwarf planet orbiting the Kuiper Belt, has a bizarre elongated shape and 2 moons. The day on this planet lasts 4 hours, making it the fastest spinning large object in the solar system. But the most mysterious thing about Haumea is that the planet has a thin 40-mile-wide ring circling it. Astronomers haven't managed to figure out how or why it appeared around the dwarf planet. 11 Earths could fit across the equator of Jupiter, and if our planet was the size of a grape, the gas giant would be as large as a basketball. 9 spacecraft have already visited Jupiter. 7 of them just flew by, and 2 orbited the huge planet. The most recent of them, Juno, arrived at Jupiter in 2016. The craters of the moon's south pole are likely to be the frostiest place in the whole solar system. The craters' floors are always in the shadow. That's why the temperature never rises above 397 degrees Fahrenheit, even during the day. If you decided to fly a plane to Pluto, your journey would take around 800 years. You'll find the highest mountain in the solar system on an asteroid called Vesta. Its peak rises 14 miles above the base of the mountain. This makes Rye Sylvia, that's what the mountain is called, almost 3 times taller than Everest. Saturn's rings weren't discovered all at once. It happened gradually. That's why they were named alphabetically in the order scientists found them. Now they go like this: D, C, B, A, F, G, and E. A day on Venus is around 243 Earth days long. But the bad news is that you'd have to wait for a weekend for 3 years. All because a day on Venus is longer than its year. A solar phenomenon called terminator events is taking place at the sun's equator. Disastrous magnetic field collisions seem to cause ginormous twin tsunamis of plasma. These tsunamis tear across the star's surface, moving at a speed of 1,000 feet per second. They can last for weeks at a time and happen almost every decade. The winds on Neptune are the fastest in our solar system. Most of them can reach the speed of 1,600 miles per hour. Almost any of these enormous storms could easily swallow our entire planet. The 18th brightest star in the night sky, Fomalhaut, is a terrifying sight. It's dubbed the Eye of Sauron because a ring of dust and debris circling it makes it look like a giant eye staring into your soul. The intimidating star is more than twice the mass of our Sun and is 25 light-years away from Earth, which isn't that far away considering distances in space. Mars has 2 moons, Phobos and Deimos. In the next 30 to 50 million years, the planet's gravitational forces will tear Phobos apart. It'll probably result in the formation of a ring around Mars. An asteroid the size of a car enters the atmosphere of our planet every year. Such an intruder could wipe out a small town off the face of the Earth. Dust and smoke would rise into the atmosphere, preventing sunlight from reaching the surface of the planet. It would cause the temperatures all over the world to drop and the climate would change. Luckily, such asteroids burn in the atmosphere before they even come close to the surface. The radio signal produced by a spacecraft when it contacts Earth is less powerful than a light bulb in your fridge. By the time this signal reaches our planet, its power is only 1/1000th of a watt. No wonder that antennas gathering these super weak signals are huge. The Deep Space Network that detects signals from spacecraft has dish antennas that measure up to 230 feet across. That's more than the width of a soccer field. In 1999, NASA lost a Mars orbiter because one engineering team was using the metric system, and another was doing calculations with the help of the imperial system. Nebulas are giant clouds of gas and dust. With time, gravity starts to pull these clumps of dust and gas together. They grow larger and larger. And their gravity gets more powerful. One day, a nebula's mass becomes so great that it collapses under its own gravity and forms a new star. Around 4,000 light-years away, in the constellation of Scorpion, there is the Butterfly Nebula. Its wingspan is greater than 3 light-years, and the structure inside the nebula is one of the most complicated ever observed. The nebula's central star, a white dwarf, is heated to an insane 450,000 degrees Fahrenheit. This means it was formed from another huge star, likely more than 5 times the size of our Sun. The white dwarf is surrounded by a thick disk of dust and gas at the equator. That's what probably makes the whole structure look like an hourglass, or a butterfly. If you decided to lump together all the known asteroids in the solar system, their total mass wouldn't exceed even 10% of the mass of our moon. A cloud of water vapor is floating in space. It surrounds a supermassive black hole 12 billion light-years away from Earth. The cloud contains 140 trillion times the entire volume of water on our planet. Astronomers think this water cloud appeared just 1.6 billion years later than the universe itself. The densest objects in space are neutron stars. They're the size of a small city, yet their mass is about 1.4 times the mass of our Sun. A single teaspoon of neutron star material would weigh 1 billion tons. And a neutron star's gravity is 2 billion times stronger than the gravity of our planet. In 1993, the Galileo probe was traveling past a miniature asteroid. It was no more than 20 miles across, and still, the tiny thing had a 1-mile-wide moon. Astronomers have discovered tons of moons orbiting minor planets in the solar system since then. We live inside the Sun. The star's atmosphere stretches way beyond its visible surface, and our planet is well within its reach. That's how the gust of the solar wind creates such a breathtaking phenomenon as the northern and southern lights. The center of the Milky Way is a story of intense radiation, gravity, and mystery. A place where the forces of nature are pushed to their limits. But what if our own planet were to find itself in this cosmic theater? What would happen if the Earth were located there and somehow managed to survive? Let's start this journey to the heart of our galaxy and find out. Picture this. You're floating in space, surrounded by billions and billions of stars. Suddenly, you see a bright swirling mass of gas and dust in the distance. That, my friend, is the Milky Way galaxy, our home in the vast expanse of the universe. The Milky Way is estimated to contain over 100 billion stars and is about 100,000 light-years across. In other words, if you were traveling at the speed of light, it would take you 100,000 years to cross the Milky Way from one end to the other. It's a couple trillions of miles. And it isn't just a static collection of stars and gas. It's a dynamic, evolving system. In fact, the Milky Way is currently hurtling through space at a speed of about 1.3 million miles per hour. One of the most fascinating things about our galaxy is its shape. The Milky Way is a spiral galaxy, which means that it kinda looks like a disk with a central bulge and spiral arms. The spiral arms are the areas where new stars are born. It's where the most stars, gas, and dust are concentrated. And this is where the solar system is located. Our system is like a tiny speck in the grand cosmic tapestry of the Milky Way. It's about 26,000 light-years away from the center of the galaxy. A pretty long distance, isn't it? The solar system is also moving through the Milky Way as it orbits around the galactic center. It takes about 230 million years for our system to make one complete orbit around the galaxy. Just imagine that. Since the time of the dinosaurs, we've traveled just a quarter of this way. The position of the solar system in the galaxy affects our life in many ways. For example, things like the amount of radiation and cosmic rays we're exposed to, and even the likelihood of asteroid impacts, and so on. Also, thanks to our location, we can enjoy some pretty amazing views of the universe around us. From our vantage point in the Milky Way, we're able to see other galaxies, nebulae, and star clusters in breathtaking detail. We're also a part of a pretty happening neighborhood, with lots of other stars and planets nearby, so we're lucky fellas. But what would happen if we weren't so lucky? What if the Earth was located in the center of the Milky Way instead? The center of the Milky Way is home to a region of space called the central bulge, and it's just packed with stars. It's like a disco ball, but instead of shiny mirrors, it's covered in stars. Only this disco ball is really huge, about 10,000 light-years in diameter. The center of the Milky Way is also home to some extreme environments that would make even the bravest astronauts shiver. High-energy particles and intense magnetic fields can wreak havoc on electronics and spacecraft. Intense radiation fields can fry anything in their path, so it's not exactly a friendly place for life as we know it. So, if the Earth were located somewhere closer to the center of the Milky Way galaxy, it would be a very different place. Let's take a look at some of the potential effects. First of all, radiation. As we mentioned earlier, the center of the Milky Way is one of the most radiation-dense regions in the galaxy. It would make life on Earth very challenging, if not impossible. Sure, we have the Earth's magnetic field. It's like a giant shield that protects us from harmful radiation from outer space. But could it protect us if we were located in the center of the Milky Way? Unfortunately, the answer is no. It's kind of like trying to use a tiny umbrella to protect yourself from a massive storm. So it would be an easy win for the galaxy. But it's not all doom and gloom. There are some brave organisms that are able to adapt to high levels of radiation. We've seen that life on Earth has evolved to survive anywhere, from the depths of the ocean to the icy poles of the planet. So, let's imagine what would happen if we somehow evolved to survive in these harsh conditions. Like, picture humans with tough, scaly skin that protects them from radiation, and plants with unique structures that allow them to thrive in this bright environment. In that case, radiation could still have some seriously spooky effects on us, For example, it could damage DNA molecules and cause mutations. Imagine a world where plants grow with 5 leaves instead of 4, animals have strangely colored fur, or people have unusual eye colors or other unique features. And these are just some of the best examples. Let's not dive into the bad ones. Also, it could cause us to undergo some metabolic changes. Maybe our bodies could process food and other resources more quickly, which could lead to faster growth rates and larger sizes. Plants could grow tall and thick, and animals would be much larger than usual. There are also some organisms on Earth that are able to bioluminesce. Thanks to high levels of radiation, these organisms could potentially glow even brighter than usual. Imagine walking through a forest at night and seeing trees, mushrooms, and even insects glowing with an eerie blue or green light. Frightening and amazing, isn't it? But let's move on to the next big change: gravity. The gravity in the center of the Milky Way is incredibly strong, all thanks to a supermassive black hole, which is about 4 million times the mass of the Sun. This black hole is called Sagittarius A. And yep, it's our neighbor now. Great. And assuming we don't get swallowed by this black hole or crushed by this incredibly strong gravity, it still could trigger lots of earthquakes and volcanic eruptions. This black hole would be like the gravitational bully, pulling and tugging at everything in its path. Basically, if we survive this, we'd have an epic surfing competition every single day. Just add a bit of the thrill of risking your life, and forget about running away from the planet. No easy rocket launches anymore. And physical objects won't be the only ones affected by gravity. Time would flow very differently for us. According to Einstein's theory of relativity, time passes more slowly in areas of high gravity. In other words, Earthlings would age more slowly than someone far from the center of our galaxy. Also, the center of the Milky Way is a very busy place. Stars, planets, and other celestial objects moving around at incredibly high speeds there every day. The positions of stars and other objects would be constantly changing. In other words, say goodbye to normal navigation. The GPS system would likely be unreliable due to the strong gravitational forces and high radiation. So, if you accidentally got lost in a glow-in-the-dark forest with some creepy animals, good luck. But it's not all bad. The center is also home to molecular clouds. These are the regions of space where new stars are born. And the Milky Way in general has some pretty amazing sights to offer. For example, stunning nebulae like the Orion Nebula and the Eagle Nebula, which are visible with telescopes or even just a good pair of binoculars. So, if Earth were located in the center of the Milky Way, we would have a front row seat to some of the most spectacular cosmic events. Wouldn't that be awesome? Overall, if Earth were located in the center of the Milky Way, it would be a very different place. Of course, we all understand that our planet wouldn't have survived such a change. But it's still pretty interesting to imagine how our life would flow if we were there. And judging by what we just discussed, it wouldn't be pretty. So let's treasure and appreciate our small, quiet solar system. There are a lot of unanswered questions in physics. How did universal energy and matter appear? Where did gravity come from? And much more. We've been trying for years to get answers to these questions. And one of the people who tried to do this was Paramahamsa Tiwari, the author of the so-called space vortex theory. What is this theory, and what does it say about the hidden laws of our universe? Let's figure it out. Paramahamsa Tiwari was the former executive director of the Nuclear Power Corporation, India. He took the space vortex theory, or SVT for short, first proposed by René Descartes and finalized it. He was always inspired by physics and its greats, even since his days as an electrical engineering student. After rigorous studies of the laws of physics, he discovered new equations defining matter and the mass and charge of the electron. After that, he came up with the SVT. This theory tried to explain the unexplained phenomena in physics. including the creation of the electron and gravitational, electrostatic, and electromagnetic energy fields, as well as other things. It also described the 6 hidden laws of the universe that underlie our entire world. But first of all, let's talk about the theory itself. Space vortex theory suggests that the universe is made up of vortices, or swirling patterns of energy. And according to SVT, these vortices are the fundamental building blocks of the universe. They're the driving force behind the laws of physics and the fundamental principles of our world. Basically, everything in the universe is connected and interconnected through these vortices. This theory isn't very based on any real observations, but rather on mathematical models and computational modeling. For example, some computational models showed how these vortices work in hydrodynamics and plasma physics. They showed that vortices in such systems can have a central point of attraction and can be interconnected. Other models were used to study how the energies inside the vortices move and how they can create different frequencies and vibrations. But some experts have criticized SVT for using only models and simulations. The biggest criticism is that this theory can't actually be tested. It relies on mathematics and not on some experimental data. That's why it's not accepted as a mainstream scientific theory. But it's still quite interesting and provides a unique perspective on the universe and our understanding of the laws of physics. For example, according to SVT, the universe has some underlying hidden rules that cause the creation of fundamental matter, their assembly, and movement. What are these laws and what do they say? Well, let's take a look at them. Law 1. The universe has only one primordial entity, space, i.e. absolute vacuum, that structures matter. This law states that space is the fundamental building block of the universe and that it's responsible for structuring matter. It suggests that space is the fundamental entity that creates and maintains the structure of matter, and that all matter in the universe is made up of the same fundamental particles, like electrons and positrons. Let's try to put it in simple words. Imagine that the universe is like a big Lego set. Just like how all the Lego bricks are made up of the same basic building blocks, the universe is made up of the same fundamental building blocks too. And these blocks are called electrons and positrons. But what holds these blocks together? Space, of course. Space gives it shape and structure, just like how the plastic container holds all the Lego bricks together in a set. So, the first law states that space is the fundamental building block that structures matter and holds everything together in the universe. Law 2. Matter is constituted with multiples of only one kind of fundamental particles, electrons and positrons. This law states that all matter in the universe is made up of the same fundamental particles, the electron and positron. These two are the Lego blocks we've talked about before. And according to the second law, these tiny invisible particles make up everything from a tiny atom to a giant galaxy. Just like no matter what the shape or size our Lego build is, it's still made up of the same building blocks. Law 3. The field distribution in space, as recognized by contemporary physics, linked with and emanating from matter, are effects arising from only one fundamental field in space. This law states that the fields recognized by contemporary physics, such as the electromagnetic and gravitational fields, are effects arising from a single fundamental field in space. It suggests that this fundamental field is responsible for creating everything that we observe in the universe. So let's try to put it simply. This time, imagine that the universe is like a big playground. All the different fields we observe, such as the gravitational and electromagnetic fields, are like different games we play in there. But no matter what we play, we're still in one fundamental space. This is the playground itself. It's the base that holds everything together. According to the third law, without the playground, we wouldn't be able to play any games. And without this fundamental field in space, we wouldn't be able to observe any fields in the universe. Law 4. There is no void in space anywhere in the whole universe except at the centers of the fundamental particles of matter, electrons and positrons. This law states that there's no truly empty space in the universe and that all space is filled with the fundamental field, the one we talked about before. It says that electrons and positrons can be found everywhere, and even the things we consider to be empty, like vacuum, are actually full of tiny particles. And according to this law, the only truly empty spaces we can find in the universe are at the centers of the fundamental particles, electrons and positrons. Law 5. From only one fundamental universal constant, all the constants considered universal in contemporary physics are derivable. This law states that all the constants considered universal in contemporary physics can be derived from a single fundamental universal constant. It suggests that all the constants in physics are interconnected and can be explained by a single fundamental principle. I know you've been doing a lot of imagining lately, but bear with me. This time, please imagine the universe as a big recipe. All the constants in physics, such as the speed of light, the gravitational constant, and the Planck constant, are like the ingredients. They're very different and there are tons of them. But just like how all the ingredients in a recipe are interconnected and come together to make one dish, all the constants in physics come together to make the universe. And just like how a recipe has a main ingredient that holds everything together, physics also has a single fundamental constant that holds everything together. Law 6. The spatial structure of submicrocosmic fundamental matter is repetitive uniformly in the spatial structures of macrocosmic bodies like planets, stars, and galaxies. This law states that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales, from subatomic particles to macrocosmic bodies like planets, stars, and galaxies. It suggests that the same fundamental principles govern the structure of matter at all scales. Let's go back to the analogy with the recipes and cooking. Using different ingredients and combining them in different ways, the chef can create new dishes. These will all be different dishes and they can be very simple or very complex. But when creating them, the chef still applies the same basic rules and knowledge they have, right? And just like that, the universe also creates different structures, from atoms to planets, stars, and galaxies. But it still uses the same fundamental principles to create all these things. So, this law suggests that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales. These are the 6 fundamental laws of the universe according to the SVT, and even though it's not accepted by mainstream science, it's still a pretty interesting concept.
In the heart of the galaxy, there lies a mysterious object, the likes of which no astronomer has ever seen. It streaks across the sky like a shooting star on caffeine. So, what is this mysterious blob? And how is it related to the black hole in the center of our galaxy? Let's find out. This thing is called X7. It's the mysterious blob that's been hanging around our galaxy's supermassive black hole for decades. Some even say it's been lurking around there for, hundreds of years. We know a few things about X7. For example, it weighs around 50 times as much as Earth. It may sound like a lot if you're an Earthling, but in space, that's like a tiny drop in the ocean. X7 is also moving pretty fast, at speeds of up to 700 miles per second. That's faster than you trying to catch the last slice of pizza before your roommate gets to it. But what in the world is this thing? A magic star we've never seen before? An extraterrestrial spaceship? Well, there are some theories connected to the blob's future tragic fate. Unfortunately, X7's days are numbered. Right now, it's on a 170-year-long elliptical orbit around the supermassive black hole at the center of the Milky Way. But it's not going to make it that far. Each year, it's spiraling closer and closer to the black hole. In just a few years, it will become spaghettified. Yes, that's a real scientific term. And finally get sucked in, never to be seen again. There are supermassive black holes in the centers of all galaxies, including our very own Milky Way. These black holes are so massive that they warp space-time, causing nearby stars to orbit around them at incredible speeds. They serve as cosmic vacuum cleaners that suck in anything and everything that comes close enough. The black hole in our galaxy is called the Sagittarius A star. Sounds like the name of a fancy Hollywood celebrity, doesn't it? But this celestial object is far more impressive than any mere mortal. It's about 4 million times more massive than our sun, which means it could probably eat our entire solar system for breakfast. But don't worry, these black holes may seem really scary, but in reality, they're too small to compete with an entire galaxy. They'll just suck in a couple of the nearest stars, and that's all. Also, Sagittarius A star doesn't seem to have a very good appetite. It's been observed to be pretty quiet lately, which is good news for us. But even if it were super greedy, it wouldn't pose any threat to us. This black hole is over 26,000 light years away. From Earth, we can see it in the Sagittarius constellation. In 2022, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A star. It took years of collaboration and technology to capture this stunning image. And this is our second photo of a black hole in history. The first one was released in 2019, and it showed the supermassive black hole called M87 star. Yes, they both have star in their names. Don't try to make it make sense. Anyway, you may remember this photo as the first ever image of a black hole ever. It went crazy viral across the internet. And this black hole, M87 star, located in the Messier 87 galaxy, is way scarier than Sagittarius A star. You thought 4 million solar masses is impressive? Then how about 2.5 billion solar masses? M87 is a real monster. It's also known for its powerful jets of plasma, which are so energetic that they extend thousands of light years from the black hole's center. If M87 were a superhero, it would be Iron Man, with his repulsor beams on full blast. Now technically, you can't take a photo of a black hole itself, since it's, well, black. No light can escape its grasp. But the glowing orange ring in this photo shows the matter surrounding Sagittarius A star. It's called the accretion disk, a swirling disk of hot gas that spirals the center, heating up to millions of degrees in the process. It's like a giant fiery vortex, but with no escape. And the shadow in the center indicates the black hole itself. Inside that shadow, there's an event horizon. The event horizon is the boundary around the black hole, beyond which nothing, not even light, can escape its gravitational pull. It's the point of no return, where the gravitational force is so strong that even the fastest object in the universe, light, can't escape. Once you cross the event horizon, you're doomed to fall toward the center of the black hole, where the laws of physics as we know them break down. And this is exactly the fate that awaits our unfortunate X7. Right now, the pure blob is getting stretched and yanked by powerful tidal forces. By the way, before it meets its untimely demise, X7 is expected to put on a bit of a show. Its closest approach to the black hole, called periastron, is projected to happen in 2036. And when it finally gets torn apart by the Sagittarius A star's gravitational forces, there may be some cool fireworks to see. But this is not the most important thing. The funny part is, X7's future end may help us finally understand what the heck even is this thing. A team of scientists have been studying how a strange blob orbits the black hole. And that's when they discovered that X7 has stretched to almost twice its initial length. And what does that mean? Well, It suggests that X7 is most likely made of debris ejected during a recent collision between two stars. Yep, you heard that right, a space car crash. Imagine this. Two stars fall in love and start circling each other for many years. After that, they finally merge together. At this moment, they eject tons of gas and dust. And perhaps this cosmic dance created our blob baby, X7. It's basically like the crumbs left on the table after a giant space feast. Something like this is actually pretty common, especially around black holes. It's like a galactic fender bender that sends debris flying everywhere. Actually, the universe is full of mystery blobs. They're called the G objects. No, they're not the G-men from Men in Black, but they're just as mysterious and elusive. These guys have been puzzling astronomers for more than 20 years. They look like gas clouds, but behave like stars. It's like they can't decide whether they want to be a cloud or a star. Come on, guys, make up your mind. G objects stretch out at the closest point to the central black hole, but emerge intact, like a rubber band that stretches but doesn't break. Scientists think that they're the stars that have merged together into one. And while doing that, they also produce a huge cloud of gas that hides the result from view. Kinda like when you're wearing a bulky sweater, so that no one knows that you've put on a few extra pounds. And then a study published in 2021 found that one of these objects, G2, was actually a molecular cloud concealing 3 baby stars. Talk about a plot twist. But X7 is the black sheep of the strange blob family. It's significantly different from the G objects, like the weird cousin you see once a year at family gatherings. Its evolution has been more dramatic. Also, it's not being held together by a mass lurking in its center. So what is it being held together by? Pixie dust? Magic? We need answers! That's why scientists believe that X7 isn't a G object itself, but debris left from it. Or maybe not. We have no idea. The possibilities are endless, and that's what makes astronomy so exciting. So let's keep our eyes on the skies and see what other strange objects are out there. Who knows? Maybe we'll discover another mystery blob, and this time it's going to be a spaceship. Now that would be awesome.
You know how galaxies have supermassive black holes in their centers? In most cases, we don't have to be afraid they'll come after us. They stay at the same spot for eternity, or at least until they start to evaporate and give the energy they have stolen back to the universe. But there's always that one rebel that spoils the statistics, like this invisible beast that ran away, moving farther and farther from its home galaxy. It escaped with style though, leaving a shiny trail of stars behind it, like a wake behind a ship. And it's moving really fast. If it was somewhere in our solar system, the moving black holes could cross the distance between our home planet and the moon in a mere 14 minutes. A regular spacecraft needs 3 days to do that. The unusual space wanderer weighs as much as 20 million suns and has left a trail of newborn stars 200,000 light-years long, which is twice the diameter of our galaxy. No one has definitely seen anything like that before. There are a few ways a supermassive black hole can run away from its home. One of them is when two galaxies come together in a big collision. As they hit each other, you get a pair of supermassive black holes that start dancing in circles around each other. If there's one more black hole that decides to join the party, it can give a big push to one of the dancers and kind of catapult it far away from the center of the galaxy. Another way is when the two dancers finally catch up with each other, align their moves, and become so compatible they merge at one point. This new black hole they create can get a push or a kick, and before it even knows it, it's somewhere far, far away from the safety of its home. This runaway black hole we're talking about is probably the result of many collisions of giant black holes. Their home galaxies probably merged around 50 million years ago, which brought these two together. Then, an intruder likely appeared, another galaxy with its very own giant space vacuum. and things quickly became chaotic. As one of those three tried to steal the moment from the other two, it ended up thrown out of the galaxy. The original pair may have stayed there, or maybe the guest took the place of one of them. Don't think it's always that easy to go after the rebel and talk it into going back home. It's generally really hard to detect black holes. Sometimes they give away their current position when they eat large volumes of stuff they find on their way, such as gas and stars. When they're full, they become very bright, but the rest of the time, they just eat a normal amount and hide in the eternal shadows of the cosmos. They leave traces when they come closer to objects in space. We may not be able to see black holes directly, but special telescopes can catch what they do to their environment. For example, we can observe a star that makes circles around something we can't see instead of orbiting its binary companion star as we'd expect. Scientists can measure how fast that star is speeding up and calculate the mass of the object that's pulling on it. And when the mass is so big they can't match it with anything they know about, it means it's probably a black hole. Also, special X-ray telescopes can recognize radiation emitted by a star that has come too close to a black hole, which is now pulling it apart with its strong gravity. Black holes have an accretion disk, which is like a swirling thing that orbits them, like a whirlpool. When stuff from their surrounding falls into this whirlpool, it gets very hot and starts shooting out X-rays. Supermassive black holes have a mass of over 1 million suns, so it's not surprising they shoot out gas particularly far into space, sometimes even millions of light years away. Anyway, our rebellious black hole was hard to spot, considering how it kept moving faster and faster. But unlike others, it's never tried to hide, considering that shiny trail of stars. It doesn't gobble up stars that are ahead of it. Obviously not a fan of Pac-Man. Poor fella doesn't even have time to stop and grab a quick bite. Instead, it's just plowing into gas in front of it, which triggers the formation of new stars along its narrow path. The gas probably cools and forms a trail that's nearly half as bright as the galaxy itself. The black hole sits at the top of the column that stretches all the way back to its parent galaxy. It seems like this runaway wants to mark the way wherever it goes, in case it ever decides to get back home. And over there, at its tip, there's a glowing knot of ionized oxygen. It's probably there because it got shocked and heated from the black hole moving and hitting the gas. Or maybe this could be radiation coming from the accretion disk. This is not the only unusual black hole traveler that decided to take a different path in life. Astronomers have found another wanderer, a black hole, completely on its own for the very first time. Big stars can explode and turn into black holes, but in most cases, these black holes have star companions. When they come in a binary system, they interact with their partner so you can find them easier because of the light around them. That's why finding this solo traveler wasn't easy at all. It just didn't give off any light. But the Hubble Space Telescope did a pretty good job of finding how the gravity of this sneaky black hole bent light around it, similar to how a magnifying glass does. It's cool that we found something like this because it tells us there could be more of these loners that prefer traveling alone, hiding in the dark. These black holes sound scary, but the comforting thought is they're very far away. Take this lonely wanderer as an example. It's 5,150 light-years away from our home planet. But in 2020, scientists thought that they had found the closest black hole to Earth, only 1,000 light-years away from us. It was really big news until they realized they had actually fallen for an optical illusion. They thought there were 3 giant things over there. A big star making a circle around a black hole every 40 days, with one more star whose orbit went way farther. But it seems it was just a system of 2 stars orbiting each other closer than expected. But we've still got something cool to observe, because they're so close that one of the stars is pulling the atmosphere off the other. Yup, stars have their own vampires too. This vampire star is way bigger and spins faster than the other one. This results in an illusion that they're orbiting each other farther apart than in reality. Still, if I had to choose between these vampire stars and J114 in our galaxy, I'd definitely choose them. The latter one is a terrifyingly big black hole about 3 billion times heavier than our Sun. Our planet is not even a crumb in its morning bowl of cereal since it eats chunks of matter as big as the whole Earth every second. We're talking about the brightest and fastest growing black hole we've seen in the last 9 billion years. What's also fascinating is that this black hole devours matter so quickly that its boundary, which we call the event horizon, is really wide. You could easily fit all the planets of our solar system inside. The cool thing is also that its event horizon is so bright, even amateur astronomers with good telescopes can see it if they look for it in the right part of the sky.
Now, when we say the word universe, we're already picturing this vast space filled with stars, planets, and comets. Truth is, most of us find it hard to actually picture how large the universe is. Well, try to think of space as the biggest playground you've ever seen. Right now, our space playground goes on for 46 billion light-years. It wasn't always like that. On that note, you've surely heard of the Big Bang Theory. Let's try to unpack it. Imagine the whole wide universe, every star, planet, down to the smallest particle, squished into a tiny super-hot ball the size of, let's say, an apple. From that point on, we've got a pretty neat roadmap of how things unfolded in the cosmos. Dive even deeper into the universe's past, and things start to get a bit blurry. The energies and temperatures rise, and suddenly, our rulebook of physics doesn't make sense anymore. When we reach these early times, gravity, that force that keeps our feet on the ground, starts acting all mysterious. This is where we bump into the great puzzle of our time, quantum gravity. And here's the honest truth, we've still got some homework to do on that one. What made the Big Bang go pop in the first place? Well, it's kind of like asking what happened before the first page of a book. There's no page zero, or at least that's the answer that quantum physics provides. It tells us that there are events in the universe that just, happen. It's not because we're not looking where we should, it's just how the universe works. Or at least, that's our current understanding of it. Right after the blast, everything was just a bubbly mix of gas, like this soda can that just got opened. This gas, which was mainly helium and hydrogen, began to stretch out and cool down. If we could time travel to those times, we'd see a younger, hotter, and cozier universe. Cool telescopes like the Hubble and James Webb let us peek into those ancient times. And what we see is fascinating. Earlier galaxies were like the cute photos of the universe when it was younger. Tinier, less heavy, and not as evolved as they are now. Over billions of years, the universe stretched out like a soap bubble. Imagine countless shiny marbles inside it, representing stars and galaxies. As the bubble grew bigger, the marbles spread out. Today, inside our bubble, we have trillions of galaxies. For every single galaxy we can spot, there are tons more we haven't seen yet. Some are too tiny, others are too far away. We still can't see them even if we use the fanciest telescopes available. Just to paint you a better picture, know that today our very own Milky Way is home to around 400 billion stars, similar to the Sun. It was a lot different in the past, though. Our galaxy began its journey like a little bundle of stuff, just a tad denser than most things in space. A lot of it was actually made of dark matter. Our closest star friend, named Proxima Centauri, is 4.2 light-years away. To put that in earthly terms, that's like taking a road trip around our planet millions of times. It's also about the same age as the Sun. If we could have looked at the exact spot about 5 billion years ago, it wouldn't have been there at all. Many stars live together in groups, kind of like families. However, most are solo adventurers, experiencing the vastness on their own. When you zoom out from our Milky Way and peek into the larger universe, it's more, empty, like a vast piece of countryside between big cities. In our cosmic area, we've got some cool neighbors. The Andromeda Galaxy, for instance, is just a stroll away, in cosmic terms, at 2.5 million light-years. And there are lots of smaller galaxies too, like the Triangulum Galaxy and the Large Magellanic Cloud. Our local hangout spot, which includes all these galaxies, spans about 3 million light-years. As we explore further, galaxies seem to gather in clusters, like suburbs. Connecting these clusters are threads of galaxies, creating a giant web in the universe. Galaxies are clustered this way because, just like magnets, they love to pull stuff towards them. If we could turn back time, we'd see a different picture. That's because throughout history, the popular galaxies with lots of stuff became even bigger, while the less popular ones gave their items away. From Earth, we can only see objects that are 46 billion light-years away at the most. If we put all this space into a giant box, its volume would be unimaginably huge. The main reason our universe is such a grand spectacle today is that it's been growing nonstop. Every year, its size increases a little more. In fact, the universe is expanding faster than the speed of light. Sure, we can't feel it down here on Earth, but there are clear signs in the universe that it's happening. We're still not sure why the universe behaves like that, but scientists are working hard to figure out this mysterious expansion. Our understanding of the universe has changed a lot over the years, too. Back in the day, when our world had more trees than buildings, people from all corners of the Earth would gaze up at a twinkling sky above. For many, the sky was their roadmap, alarm clock, and spiritual connection point. Now, imagine not having a smartphone or a compass, and still being able to find your way home or knowing when to plant your crops. That's because our ancestors had the sky. They knew when it was time to take care of plants, navigate ships, or celebrate special occasions, all by watching the stars and planets. Long ago, people in Babylon spotted some stars that behaved a little weirdly. These stars seemed to have a mind of their own. Obviously, we know now that they weren't stars at all. They were planets, like Venus and Mars, that sometimes wink at us down here. There was also a time when we believed the Earth was flat. Well, at least some people did, before Greeks in the 6th century BCE figured out that it's round. They even managed to guess its size by watching shadows in different places. They were pretty close with their estimations, especially if you take into consideration their limited tools. Now, speaking of our planet, there was also a time when humankind believed the Earth to be the center of the universe. We also believed everything else was just spinning around it. That was until a man named Copernicus did a bit of research and figured out it was actually the sun coordinating all the movement in our system. And soon after, other thinkers and stargazers joined in on the fun, changing how we perceive the universe using new tools. Speaking of tools, thanks to a telescope, Galileo found out that Jupiter had massive moons tagging along. We call them the Galilean moons today in his honor. But the universe kept tossing surprises our way. Some people started cataloging stars, clusters, and nebula, while others found mysterious rays that our eyes can't see. And just when we thought we had it all figured out, Edwin Hubble, not the telescope but the man behind the name, discovered something amazing too. He realized that other galaxies are in fact moving further away from us. These days, we're looking at the universe in a different way. We know how the timeline works now. We know that our time here on Earth is limited. No wonder astronomers are eagerly scouting through the vastness of space, looking for planets similar to ours. There is no other planet that can safely accommodate us in our solar system. But we can use our neighboring planets and satellites for scientific purposes. Take Mars, for instance. In the following decades, NASA is planning to send all sorts of devices and even people up there. If the experiment proves to be successful, we might end up living there for a while, or at least use it as a pit stop for our next exciting destination.
Imagine the universe as a gigantic, elastic balloon that's steadily being inflated. That's what dark energy seems to be doing, forcing galaxies further apart. Could this force lead to the end of the universe? Some scientists do think so, and they've named this potential event the Big Rip. It's challenging to study dark energy, even though it's one of the most fascinating aspects of our cosmos. That's because its only visible effect is this gentle stretching of space. On any smaller scale, it's virtually undetectable. Compared to dark energy, studying dark matter feels like a walk in the park. Even though it's just as invisible, dark matter leaves clear evidence of its existence. It latches onto galaxies and galaxy clusters, bending light and altering gravity. Dark energy, on the flip side, just expands. Nonetheless, scientists have found ways to examine it, mostly by observing the universe's expansion. As we peer into the distance, we are, in fact, peering back in time, tracing the universe's evolution. Dark energy could also bring about the end of the universe in a massive, catastrophic event. Imagine watching helplessly as reality itself tears apart with no hope of escape. Frighteningly, it's not some far-fetched scenario. The available data does not eliminate the possibility of a big rip. Is dark energy a force that keeps inflating the universe, or is it more like a separator? If two galaxies are far away from each other, they're driven further apart, leading to increasing cosmic isolation. But anything that's already a strong structure stays intact, immune to this divisive force. Why doesn't it mess things up, you ask? Well, it's because dark energy remains consistent. As space grows bigger, the density of dark energy remains steady. Imagine drawing a circle anywhere in space, taking note of the amount of dark energy there. Do it again after 1 billion years, and guess what? The amount of dark energy inside your circle won't change, even though space itself has expanded. That is, unless, of course, dark energy has a trick up its sleeve and proves to be more potent than a cosmological constant. All we know for sure is that it's something that drives the universe to expand more rapidly. Or to put it another way, it creates negative pressure. Now, negative pressure might sound odd. Pressure is usually seen as an outward force, right? But in the universe, it behaves differently. Pressure is a type of energy, like mass, that attracts rather than repels. All these calculations are what makes the Big Rip picture a slow, unraveling movie. The first objects affected are the most massive, loosely bound structures, like giant clusters of galaxies. Their gravitational pull will start weakening, causing them to drift away into the growing cosmic voids. Next, we'd notice stars on the outskirts of our galaxy not following their usual paths, but instead drifting away, like party guests saying their goodbyes. The night sky would then start to dim as our Milky Way would gradually evaporate. The disaster would just accelerate from there. The orbits of the planet would begin to shift, spiraling outward. Just months before the end, after we've lost the outer planets, Earth would drift away from the Sun and the Moon from Earth. We would plunge into the darkness alone. The stillness of solitude won't last, however. Any remaining structure would be destroyed because of the expanding space. The Earth's atmosphere would start to thin. Gravitational shifts would cause chaotic tectonic movements. In the final hours, Earth would fall apart. Beyond this point, the destruction would continue unseen. Nuclei, the ultra-dense cores within atoms, would disintegrate next. Black holes' dense cores would get obliterated. In the last instance, space itself would just rip apart. Bad as it may sound, we may never rule out the threat of a big rip. However, it might take so long that all cosmic structures will have decayed before it happens. A rough calculation suggests the earliest big rip could be in about 200 billion years. Technically, the Sun still has about 5 billion years before it fades away naturally. So by the time this event might happen, our solar system would have long been gone. Nonetheless, given the possible implications, scientists are placing a high priority on understanding the Big Rip. Let's be optimistic though. I mean, if we look at the universe's history, we should consider ourselves lucky. We're in what cosmologists refer to as the luminiferous era. It means that right now the universe is still pretty busy producing new stars, and we know how important these celestial bodies are for maintaining life as we know it. However, the golden age of star formation was about 10 billion years ago. Ever since that peak, the rate of creating new stars has been on the decline. Now, why is the universe taking this early retirement? It's not because it's lazy or tired. In fact, it's exactly because we're living in this expanding universe. For a new star to appear, a bunch of matter needs to be squeezed into a relatively small space. It's like trying to stuff all your clothes into a very, very small suitcase. As the universe expands, the matter is getting spread out. leading to less and less room in that suitcase for creating new stars. The Big Freeze, another theory related to the end of the universe, looks at this scenario. Stars will become endangered and then extinct species. This period of star decline is what astronomers like to call the degenerate era. It's estimated to start about 100 trillion years into the future. What'll be left in the night sky at that point? Only the hardened workers of the universe, white dwarfs, neutron stars, and black holes. White dwarfs and neutron stars, the remnants of medium and large stars that have exhausted their nuclear fuel, will eventually cool off and transform into black dwarfs. These black dwarfs are like invisible cosmic spirits, just hanging around without doing much, inert and unseen. Other neutron stars, too heavy for their own good, will stumble under their weight and collapse into black holes. Further into the future, the universe will become a black holes-only party. But even these cosmic weirdos can't cheat time forever. Black holes can fade away too. In fact, this idea of fading black holes came from a brilliant mind you might have heard of, Stephen Hawking. He suggested that black holes slowly shed energy in the form of radiation until they shrivel up like raisins and evaporate completely. Eventually, every single black hole will have evaporated. We'll be left with a universe in its twilight years, settling into its final age, aptly named the Dark Era. At this point, both light and matter will be nothing but distant memories. And then, well, nothing. If this Big Freeze theory is correct, the universe will just remain in a quiet, dark state, stretching into an eternity, where nothing else ever happens. Most of these theories seem to rely on the fact that the universe is expanding. But what exactly is it expanding into? We can't help but wonder if there's something else beyond our universe. Right now, this question is one for which physics doesn't quite have an answer for. We don't have enough facts. One suggestion is that time and space came to be with the Big Bang. That happened around 14 billion years ago, so logically there's nothing beyond the universe. However, a huge chunk of the universe is way out of our sight, existing beyond the part we can observe, which is about 90 billion light-years in diameter. Because everything's pretty much the same wherever you look in the universe, we can presume that the bits we can't see would look pretty much like the parts we can. But that's just an assumption. Now, if the universe is infinite, there's nothing beyond it, right? I mean, that's just what infinite means. On the other hand, if it's finite and growing, you'd start to wonder if there's a boundary or an edge, like a universal cliff that separates our universe from whatever is beyond it. It gets even more complicated when you realize the universe has at least 4 dimensions, 3 for space and 1 for time. And it's pretty much impossible for us to picture what that might look like.
Now, we all know that all planets are round. There are no square ones so far, and that's because of gravity. Well, roundish at least, as not all of the planets have perfect proportions. But did you ever wonder about the shape of the universe itself? Is it also round because of the same forces? Well, not really. Based on what information we have so far, the universe is actually flat? According to the principles of general relativity, space has the ability to curve. This opens the door for the universe to have 3 potential shapes: a flat plane like a sheet of paper, a closed sphere like a bowl, or an open saddle-like curve. This isn't just a matter of academic interest, you know. The universe's shape has direct consequences on its ultimate destiny. One cosmologist from Princeton University explained it beautifully. The shape of the universe is a kind of map to its past and a predictor of its future. The questions of whether the universe will keep expanding forever or collapse at some point, and if it's finite or infinite, all circle back to the question of its shape. Now, to wrap your head around this cosmic question, you need to understand 2 key elements: the density of the universe and its rate of expansion. Let's dig into this a little. Around 68% of the universe is made up of dark energy, while 27% is dark matter. The rest, which is normal matter, if you'd like, makes up the stars, planets, and other cosmic bodies we're familiar with. When we talk about the density of the universe, we're referring to the quantity of normal matter packed into a given volume of space. Now, if the universe is denser, it also has more gravity. In this case, the gravitational pull can overcome the force of expansion, so the universe curls up into a sphere. This shape is known as the closed model, where the universe ends up looking like a gigantic cosmic ball. Imagine a world that's finite but without boundaries, a contradiction for sure. In this model, an adventurous explorer could travel forever through space, never bumping into a wall or falling over an edge. Alternatively, if the density of the universe is low and not enough to halt the expansion, then space distorts in the opposite direction. This results in an open universe with negative curvature that resembles a saddle, like on a horse. Despite these two potential scenarios, most scientists agree that the density of the universe is just right, which means it expands proportionally without curving. But what does it mean if the universe is flat? It doesn't mean we're living in an infinite sheet of paper. To understand it, consider these analogies. Imagine you're in a square room, walk 10 steps to the next corner, make a 90-degree turn, walk another 10 steps, and repeat this process twice more. You end up back at your starting point, completing a square. Add another dimension to this geometry, since we're not 2D creatures, and whoopee, you have a flat universe. This analogy wouldn't hold up in a curved space. If you have a terrestrial globe at home, you might find it easier to understand this next experiment. Start by placing your finger at the Earth's equator, then trace a line to the North Pole, make a 90-degree turn, and return to the equator. Make one more 90-degree turn and walk back to your starting point. This journey only needed 3 turns, unlike the 4 turns in the flat universe scenario. Still struggling to understand? Here's another way to picture it. In a flat universe, 2 rockets traveling side by side will always remain parallel. This is in contrast to a closed universe, where the rockets will travel along the curve of space and eventually meet where they started. In an open universe with negative curvature, the rockets will gradually drift apart and never cross paths again. So, is there a cosmological crisis at hand? It seems the answer to the shape of our universe is encoded in the cosmic microwave background, also named CMB, which is like the universe's fossil record. Over the past few decades, scientists have measured temperature fluctuations in the CMB to find almost no curvature, indicating a flat universe. Now, the concept of a flat universe is crucial to the standard cosmological model. However, in late 2019, scientists from a university in Rome published a paper arguing that current CMB measurements actually indicate we're really living in a closed universe. How did they figure this out? Well, they looked at how light behaves in the universe. Specifically, they analyzed how light bends because of the gravitational force of matter in its path. Either way, apart from this finding, there's nothing else that would suggest we're living in a closed universe. Most scientists believe this recent discovery is nothing more than a statistical anomaly. But if the closed universe theory turns out to be right, it would shift decades of astronomical findings. If the universe is indeed curved, it must be so large that the observable 93 billion light-years aren't enough to reveal its curvature. It could be similar to standing in a fog, only able to see a small, flat patch of land. Yet somewhere out of sight, the horizon reveals that we live on a sphere. As we continue to probe the cosmos, we might find that the apparent flatness of our universe is just a small part of a much larger, curved cosmos. Its shape is just one of the many things we've yet to figure out about the universe. We can't quite put our finger on why the universe is even here, for instance. We do have some theories, but scientists are yet to be sure. It could be that the universe is like a pop-up, materializing out of an unstable nowhere land. Imagine the emptiest emptiness you can think of, suddenly churning out matter and energy in equal and opposite amounts that tally up to zero. For most of us, it's hard to picture that process. If we follow this theory, who's to say there's only one universe? We might be just one of an enormous collection, a so-called multiverse. For now, we'll just have to wait for the next wave of cosmic measurements to refine our theories, and for scientists to come up with hypotheses that aren't just mathematically pretty, but actually testable. Also, how could we possibly know all the secrets of the universe if we don't completely understand our own biology yet? I mean, if we did, we could, theoretically, solve all of our health problems, right? We might even be able to play around with our DNA, like this molecular Lego, and give ourselves naturally purple hair or red fingernails. Well, time for a reality check, as we're still struggling with this one too. Here's a great example: our microbiome. Our bodies, home to 10 trillion human cells, are also an active city for 100 trillion microbial cells. That's a couple of pounds of bacteria and other microbes, which we absolutely can't do without. They've set up shop in our bellies, lungs, noses, and every other hidden nook and cranny. We're like luxurious cruise ships for these tiny microbial tourists, and we still don't fully understand the implications of this symbiotic relationship. There are still a lot of things we don't know about planet Earth either. We've only ever dipped our toes into Earth's crust, never venturing more than a few miles deep. Everything else is our best guess, from remote sensing and smart physics. Believe it or not, it took us an embarrassingly long time to accept that the Earth's crust is constantly shifting, like Jenga pieces. We only warmed up to plate tectonics in the mid-20th century. We're also still trying to figure out precisely how the planet's inner engine works, and how the swirling conducting materials in the outer core create our protective magnetic field. Plus, with 4.5 billion years of geological chaos, we're sometimes better off studying meteorites or the surfaces of other celestial bodies for clues about our planet's history. Even our faithful companion, the Moon, is a bit of a mystery. Was it born from a colossal collision or some other event? We're still not sure. But hey, the fact that we still have a lot to learn is what makes life interesting, isn't it? That, and the thrill of actually finding an empty parking spot in San Francisco, or maybe even your city. I'm sure we'd all like to go back in time and save ourselves from embarrassing moments in school hallways or some decisions we'd later regret. Or it would be so cool to go back and see some of your dearest moments, or maybe even further, all the way back to the 17th century to check how people lived then. Imagine seeing what dinosaurs really looked like. Maybe they weren't that scary. Whoa, okay, they were, you win. Or imagine going back and having lunch with cave people. Hopefully, we wouldn't end up as a meal of a marsupial lion, giant hyena, or some other hungry beast that were wandering around at those times. So, you'd go back, I'd go back, our friends too. Everyone would like to take a peek into history. And we would all make such a mess. It would be so chaotic if the whole universe could rewind, let alone each of us individually. What would that even look like? I mean, we're still not sure how it all started with the universe, but luckily, we have some pretty smart people who have offered us different theories. Some say there was really no beginning, and that the universe has always existed. They believe space and time may have merged out of the universe, so we can't actually talk about how it may have been before the Big Bang, since there was no before. Scientists like Newton and Einstein used to think the universe was something static. Then, in the 1920s, people found out that all galaxies were actually moving away from one another. This led to the idea of the Big Bang, a starting point where everything was concentrated in a tiny, dense point called a singularity. And then you go back to the main question again. How did that dense point show up? One theory talks about quantum mechanics. This basically means that even empty space can have tiny particles popping in and out of existence. Maybe that's how the universe got some matter, even when it was very small. Another theory says our universe could be part of something bigger, and there are always new universes popping up. And the idea says these new universes form all the time because of some tiny changes that keep happening. So there could be an infinite number of universes where each decision we make takes us just one way to one reality. Well, you've already heard of the concept of multiverses, right? But this still doesn't tell us how it started. Another option claims that our universe goes through cycles. It doesn't have a definite beginning or end, but instead goes through phases. The cyclic universe theory says that the universe didn't start from nothing, but it came from the collision of two special objects called brains. These objects exist in a special kind of space with more dimensions than we can see. When these brains collide, it creates a lot of energy that makes the universe expand. But after some time, it starts to shrink again, like it happens when you squeeze the air out of a balloon. Eventually, the balloon gets small enough to collide with another pair of brains, and the process starts all over again. Either way, maybe someday we'll be able to travel in time, so we'll see what early space looked like, and we might find at least some of the answers. Now, NASA has a cool new thing called the Nancy Grace Roman Space Telescope. It can capture really big areas of space relatively quickly. This will help us see how the universe has been transforming since its early days. Now, you'd expect all the things in the universe to be spread out evenly, like a nice smooth soup. But no. Stars gather to form galaxies, and galaxies come together in clusters. And clusters, again, are connected by long strings of something we call dark matter. And in between these strings, there are giant empty spaces. It's like a really big spiderweb of galaxies with holes in between. And it keeps expanding all the time, we think, because of this mysterious force called dark energy. The Roman Space Telescope will help us find out more about both dark matter and dark energy. Dark matter is like an invisible glue that holds galaxies together, and dark energy is a force that makes the universe expand faster and faster. When light from galaxies that are really far away from us travels through space, there can be things in its path that can bend it with their gravity. It's like having mirrors in a funhouse. This way, scientists can figure out where the mass is located in the universe. This includes dark matter, too, which is especially hard to find since we can't see it because it doesn't give off any light. So, scientists created a simulation based on what we currently know about how galaxies form. It shows a patch of the sky that is like 10 times the size of a full moon and contains more than 5 million galaxies. The Roman telescope works together with other telescopes like Hubble and Webb to give us a more complete picture. Hubble sees different types of light, and Webb provides detailed observations. If we didn't have the Roman Space Telescope, and we'd only have to rely on others, we would need hundreds of years to study the space mysteries we're looking at now. And from 2027, with the help of the Roman Space Telescope, we'll be able to take a peek into the past. If you could really go back in time, you wouldn't see giant shiny stars scattered throughout galaxies. You'd find yourself in a sea of plasma, which is basically charged particles. And in this soup, there would be tiny knots, a bit denser than their surroundings. Because of their slightly bigger mass, they'd have a bit stronger gravitational pull. With time, these knots would grow and form stars and galaxies. And if we were to rewind and start the universe all over again, the atoms would probably merge into random variations, which means we'd get some completely different galaxies, stars, and even our solar system. It formed around 4.5 billion years ago after a big cloud of space gas and dust collapsed because a nearby star exploded. When this cloud collapsed, it formed a spinning disk of material called a solar nebula. In the middle of this disk, the material came together and created a very important object for life on our planet, the Sun. The Sun is gigantic. It was made up of more than 99% of the stuff from the cloud. In the outer parts of the disk, the material started to clump together too. These clumps crashed into each other and got bigger and bigger. Some of them became round because of their gravity. Those turned into planets, dwarf planets, and big moons. But not everything became a planet. Some pieces remained small and formed the asteroid belt. Other small leftover pieces became asteroids, comets, and meteoroids. That's how our space system and everything in it, including our Earth, came to be. Now, maybe in this new version, there would be more planets with life on them, or we'd be completely different. Maybe we'd live on a planet closer to the Sun, which means we'd need better protection from the heat so life could thrive. Maybe Earth would be giant, or in a different scenario, as small as our Moon. Maybe humans would have a completely different shape, or be not human at all. There's something interesting in physics called chaos theory. It's all about studying things that seem really random or unpredictable, even though they actually follow certain rules. It's like when you play a game and you think the outcome is random, but there are actually specific reasons why things happen the way they do. It occurs when you play pinball. The ball bounces around in different directions. Even though we understand how gravity and the force of collisions work in the game, it's still really hard to predict exactly where the ball will end up. A tiny change, like hitting the ball a little bit harder or softer, can make a big difference in where it goes.
What will the end of the universe be like? It might be 100 billion years away. But here's the real question. Should we start panicking already? Jan 11, a cosmologist, appeared at a recent screening of the captivating Netflix documentary, A Trip to Infinity. She mentioned that there would be a time when the last sentient being exists and the last flicker of thought fades away. This perspective sheds a whole new light on things. Somewhere in the vast expanse of the universe, there will be a moment when the memories of legends like Einstein and Elvis will fade away. Just imagine what that last thought would be. A brilliant pearl of wisdom, a colorful expletive. The possibilities are as endless as the stars in the night sky. Now let's take a cosmic detour and explore how we got ourselves into this peculiar predicament. As we currently understand it, our universe burst into existence with a bang approximately 13.8 billion years ago. Since then, it has been expanding at an ever-increasing pace. For decades, astronomers debated whether this expansion would continue indefinitely, or if a big crunch awaited us in the distant future, where everything would collapse back together. Everything changed in 1998 when astronomers stumbled upon a discovery. The cosmic expansion was accelerating. This turbocharged expansion was fueled by a mysterious force called dark energy, woven into space-time's very fabric. The larger the universe grows, the more this enigmatic force pushes it apart. It's eerily similar to the cosmological constant, a concept introduced by Einstein to explain why the universe didn't collapse, only to be discarded later as a blunder. But guess what? The cosmological constant turned out to be a stubborn idea that refused to fade away. And now it poses a threat to both physics and the universe itself. If dark energy triumphs in the end, distant galaxies will eventually speed away from us so rapidly that we won't be able to see them anymore. With each passing moment, our understanding of the universe will diminish. Stars will extinguish and never ignite again. It will be akin to living inside an inverted black hole where matter, energy, and information are swallowed beyond the event horizon, lost forever. The star-making days of our universe are behind us. Star formation reached its peak nearly 10 billion years ago and has been gradually declining ever since. The reason for this waning of stellar light is our expanding universe. As the cosmos grows larger with each passing day, the matter within it remains constant but gets spread out over more and more volume. To create a star, matter must be compressed into relatively small volumes. As the universe ages, fewer opportunities arise for such compression. So, in the far future, we can estimate that the last star will be born approximately 1 trillion years from now. This final star is likely to be a small red dwarf, a fraction of the mass of our Sun. Red dwarf stars have extraordinarily long lives, slowly burning through hydrogen in a steady fusion reaction, but eventually, even they will exhaust their fuel. In roughly 100 trillion years, the last flicker of stellar light will fade away. This accelerated expansion will progressively limit our view of the wider universe. Although we can still observe distant galaxies because of the light they emitted long ago, their current light will never reach us. As the universe expands at an increasing rate, the boundary beyond which galaxies recede from our view moves closer and closer. One by one, galaxies will be torn away from us by the relentless cosmic expansion, accelerating so swiftly that their light will forever elude us. Anything not gravitationally bound to us will be unable to withstand this onslaught. Only the local group, consisting of the Milky Way, Andromeda, Triangulum galaxies, and several satellite dwarf galaxies, will remain in our proximity. However, this lingering existence will be far from idyllic. Over time, our three galaxies will merge into one megagalaxy, completely isolated from everything else in the universe. In this solitary state, the megagalaxy will slowly dissolve. Chance interactions will scatter individual stars, or what remains of them, into random orbits. Some will be hurled into the giant black hole at the center of the galaxy, while others will escape into the void, never to be seen again. After an unimaginable span, no complex systems will endure. All that will be left are isolated islands drifting in an infinite expanse of darkness. To make matters worse, as thinking requires energy, there will eventually come a time when the universe lacks the energy to sustain a single thought. Eventually, all that will remain are subatomic particles, dancing in the vast expanse of intergalactic space, engulfed by eternal darkness. This will occur trillions upon trillions of years after the last glimmers of light and life have vanished. And then, countless eons will stretch onward to the point where even measuring the passage of time becomes impossible. As Brian Greene described it in his book, Until the End of Time, it's a tale full of sound and fury, signifying nothing. This might make us feel some sort of weight of insignificance in the face of this cosmic destiny. If this truly is the fate awaiting the universe, it's both humbling and disheartening. Our universe may be 14 billion years old, but that's just a fleeting moment compared to the unfathomable darkness that lies ahead. It means that everything remarkable in our universe occurred in a mere blink at the beginning, followed by an eternity of emptiness, its finality and futility on an unimaginable scale. But hold on a second. Before we surrender to despair, let's remember that we're still a long way from this inevitable end. New discoveries in physics could provide a glimmer of hope, an escape hatch from this fate. Perhaps dark energy is not constant. Maybe it will change its course and bring the universe back together. Michael Turner, the brilliant cosmologist who coined the term dark energy, emphasized that the cosmological constant would be the least interesting answer to the dark energy puzzle. So, who knows what surprises the future holds? But for now, we can't help but peer into the abyss and wonder. We are but brief inhabitants of this cosmic spectacle, here for the grand party when the universe brims with life and light. We may not have a say in the final act, but we can cherish the here and now, reveling in the magic of the present. As astrophysicist and philosopher John Archibald Wheeler once said, the past and the future are mere fictions, existing only in the artifacts and imaginations of the present. From that perspective, the universe ends with each of us, granting us a unique perspective and a chance to make our mark. So let's embrace the fleeting nature of existence. Though the future may be finite, it liberates us to fully appreciate the wonders of this moment. After all, as the saying goes, nothing lasts forever, whether it's the stock market, the stars, or even our own lives. An awareness of eternity's whiff can illuminate the brilliance of a lifetime, even if it's just mine or yours. There is more than one theory about how the universe is going to be gone forever. In the world of quantum field theory, for example, we come across something called a vacuum decay. Picture it as a vacuum that's kind of stable, but not totally rock-solid stable. This false vacuum can hang around for quite a while, chilling in its semi-stable state. Could eventually say, nah, I'm done, and transform into a more stable vacuum. We call this wild event false vacuum decay, It's like a cosmic game of Jenga, where the unstable blocks finally collapse and the universe finds its true balance. So, cosmic adventurers, let's treasure the Milky Way and all its splendor for as long as it lasts. And who knows, maybe in the vastness of this ever-expanding universe, there's still a surprise or two waiting for us. The story isn't over yet, and the cosmos is filled with secrets waiting to be uncovered. What do you think the end of the universe looks like for us humans? Are we even going to be around to witness it?
So, are you tired of boring old Earth? Want to know what lies beyond the starry night sky? You're not the only one. People have been asking the same question for centuries. Luckily, scientists have got you covered. They've discovered a lot of amazing places light years away from our blue planet. Just one light year is about 6 trillion miles. Mind-blowing, huh? So, hop on. The spaceship of knowledge is lifting off. Your first stop is 2.5 billion light years away from Earth. It's a quasar, one of the brightest objects in the universe and the first one to be discovered. A quasar isn't a star, but a distant galaxy. This extremely bright object gets its power from a supermassive black hole. A disk of matter swirls around the black hole and creates friction. It's kind of like when you're cold and rub your hands together to stay warm. The friction between the palms creates heat, making you feel nice and cozy. The same happens in the quasar, just the amount of heat is bigger, way bigger. I hope you remember to pack sunscreen lotion. The temperature at the heart of this quasar can reach 18 trillion degrees Fahrenheit. Also, there is light, a lot of it. This celestial object shines 100 times brighter than all the stars in its galaxy put together. Well, it's time to cool down a bit. Minus 457 degrees Fahrenheit, to be precise. This is the temperature of a young planetary nebula called the Boomerang Nebula. It sits 5,000 light-years away from Earth. NASA's Hubble telescope caught images of the formation in 1998. It's composed of gas coming from a star near the end of its life cycle. Inside the nebula, it's windier than in the Windy City. Winds reach speeds up to 310,000 miles per hour. And you gotta thank them for the nebula's chilling temperatures. Researchers were just impressed to find out that the temperature of the Boomerang Nebula is just 1 degree above absolute zero. 0 Kelvin should be the coldest temperature possible. This is the point where all molecular and atomic activity stops. Brr! Makes you want to crank up the thermostat in your spaceship. Next, you're going to a place you might not want to visit. Sorry. So, it's the most massive black hole. This giant is located at the heart of a large galaxy, some 10.4 billion light-years from our planet. Its mass is 66 billion times greater than that of the Sun. Enough to make our galaxy's supermassive black hole feel ashamed. It has a mass of merely 4.5 million times that of the Sun. But you better not get near any of them, as a black hole's diet consists of matter. By calculating how much matter they consume, scientists can determine their rate of expansion. And those black holes have quite an appetite. Astronomers believe there are stupendously large black holes, or slabs, hiding somewhere in the universe. If they're real, their mass is estimated to be greater than 100 billion times that of the Sun. Now, it's time to snack on something lighter. The spaceship enters the Kepler-51 system. It's home to the lightest planets in the known universe, called superpuffs. Sounds fluffy enough, and it is. These planets' mass is either the same or slightly greater than that of Earth. But this doesn't mean they're small. Think of them as giant cotton candies the size of Jupiter. They are newly born planets whose atmosphere is still cooling down. You might want to wait for this process to be over, though, as 500 degrees Fahrenheit is too hot to handle. But for experts, superpuffs are special. These planets are incredibly rare, as they've managed to discover less than 20 so far. Now, are you up for a race? Let's say the ship you're on is traveling at a speed of 25,000 miles per hour. This is the current human speed record. It was set by NASA's astronaut trio from the Apollo 10 mission in 1969. And no, I am not talking about Neil Armstrong and Buzz Aldrin. That was the Apollo 11 mission later that year. Right now, you're going to race against a star 18,000 light-years from Earth. Your biggest advantage is that this is a neutron star. It was formed when another massive star ran out of nuclear fuel and couldn't support itself anymore. Think of a car running on an empty tank. Victory couldn't be any closer, right? Well, not quite. When a massive star feels like its time is up, it shrinks and starts spinning. Figure skaters do the same during a spin. They fold in their arms to increase rotation to the maximum. This neutron star is the champion of the universe. It spins at a speed of 157 million miles per hour. That's roughly 27% of the speed of light. Whoa! Are you running low on energy at this point? Time to charge up from a gamma ray burst. Gamma rays are electromagnetic waves generated by various forms of radiation. These bursts were fairly unknown to science until the late 1960s. Satellites equipped with gamma-ray detectors accidentally recorded huge outbursts of radiation outside of our solar system. What were they? Nothing dark, definitely, as these are the most energetic forms of light. Scientists believe that gamma-ray bursts happen when two neutron stars collide and form a black hole. The other explanation is that they are in the final stage in the life of a supernova. This event happens when a star decides to go out with a bang. Gamma-ray bursts shine brighter than a diamond. They are 1,000,000 trillion times brighter than the sun. Talk about an energy boost. Your mood is lightened up by now. You want to visit a place that has a draw to it. No, it's not a beach resort, but a magnetar. It's a neutron star with a twist. Magnetars have a magnetic field that is 1,000,000,000,000 times stronger than that on our planet. But don't fall for their strong appeal. Let's just say you won't live to tell a tale if you get too close to one. In 2004, a flare that came off the surface of a magnetar managed to compress Earth's magnetic field from a distance of 50,000 light-years. Quite impressive for a star the size of a city. Makes you wish to team up with this oversized magnet to commit the greatest heist ever. A magnetar has the ability to swipe all the credit cards on planet Earth from a distance halfway to the moon. Luckily for humans, NASA has discovered only 31 of these stars so far. You have barely escaped the pull of a magnetar. Suddenly, you start to sense a strange force drawing you away from your home base. It is the Great Attractor, one of the biggest mysteries of the universe. This massive gravitational irregularity has been pulling us closer and closer to it for billions of years. Scientists estimate that the Great Attractor is located at the center of the Laniakea supercluster. The name means immeasurable heaven in Hawaiian. It represents a gigantic collection of planets, stars, and asteroids. Our home galaxy, the Milky Way, is just a speck in this enormous supercluster. According to the Big Bang Theory, not the TV show, the real theory, the universe has been expanding in all directions. But the mysterious Great Attractor is slowing things down. How exactly? Researchers still need to figure this one out. On the bright side, they are good at naming things. The end of the universe would be called the Big Crunch, if there's anyone left to call it that. Your journey, too, ends at the edge of the universe. The most distant galaxy from Earth is the oldest one as well. The galaxies that formed first after the Big Bang have drifted the furthest. So every time advanced telescopes detect a far, far away dot, they give scientists an image of the origins of the universe.
There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many, many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to -455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So, basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all. But it's still interesting to strive for it.
As soon as the Earth is cut in half, almost all living creatures will come to an end. An apocalypse will begin, which has not been shown in movies. The atmosphere is damaged, the magnetic field will change, and the planet's landscape completely alters. But the planet will be completely renewed, and life, like a phoenix, will be reborn from the ashes. A super powerful laser would be needed to separate the planet. Such a laser has to receive energy directly from the sun. The weapon goes into space on a rocket, thousands of miles above our world. Then, once the laser arrives at its destination, it opens wide to expose plates of solar panels. The laser absorbs and concentrates the sun's rays. Then a powerful energy beam with the diameter of several cities shoots into the middle of the planet. Oceans through which the beam passes boil and evaporate from the high temperature. These vapors turn into a vast thundercloud in the sky. A strong wind drives these clouds over the continents. Heavy rain falls, which floods not only cities, but entire countries. As the tectonic plates shift, tsunamis are created. Huge waves crash onto the shore. The Earth is split in two. And this is just the beginning. The structure of the Earth, or rather, each half of it, is changing. Strong earthquakes occur all over the world. The worst disasters happen near the fault line. Billions of tons of ground are smashed. Massive landslides drag entire cities below. Chunks of land, thousands of miles in size, shoot away from our planet. All living creatures on these pieces of land fly into outer space. Other broken pieces of the planet land on the half that is closest to them. Imagine a huge rock the size of a whole city falling from the sky, and there will be hundreds or thousands of such stones. Those who live far from the cut site have a chance to survive, but even there, earthquakes will destroy houses. The moon will also start to throw off pieces from itself. These pieces, like a meteor shower, will fall onto the Earth halves and create massive explosions. These explosions will create fires. The skies will be covered with ash, and until it settles, we won't be able to see the sun. Both parts of the planet are drifting away from each other. The red-hot heart of our Earth is right in the center between the two. This is the Earth's core, consisting of molten metals. Each half of the core exudes energy comparable to a star. Between the two parts of the planet, a layer of such hot space is created that nothing can survive there. Any item that falls into this space immediately turns into ashes. The mass of the core is much larger than the ground mass, so there's a higher level of gravity. The core sucks in everything that comes close. You can't travel from one part of the Earth to the other. The core's gravity attracts any shuttle. Each half of the Earth now lives on its own. Typically, the core inside our planet rotates and creates the Earth's magnetic field. This field is a shield that protects us from the sun and space. If the shield is damaged, solar and cosmic radiation passes through the atmosphere. Because the core is divided into two parts, the Earth's magnetic field becomes unstable. Power outages begin in both parts of the planet. Microwaves, TVs, kettles, traffic lights, computers, everything is broken. The screen of your laptop or phone starts turning on and off. The video may freeze and the battery runs out and charges in 1 second. Satellites stop working, which means there will be no more GPS. High-frequency radio waves used for communication stop working, which means you can't make calls and send texts. In fact, all power plants may sink underground or be flooded because of the earthquakes, so there might not be electricity at all. Some people are sensitive to solar storms and experience severe headaches. When the magnetic field is damaged, the surviving people and animals will suffer from severe migraines. Scientists will have to invent special helmets to protect people from the sun. For full protection, people will have to live in underground cities. Compass needles no longer point north. They just spin in different directions. The birds go mad. They don't know where to fly to wait out the winter because the south no longer exists for them. All animals stop migrating. In the sky, planes can't navigate. Plants and flowers can't grow naturally thanks to the increased radiation from the sun. Livestock are poorly fed. The quality of products deteriorates. There's famine. The main goal for people on each half of the planet is survival. In some places, closer to the fault, the Earth's atmosphere is completely damaged. The conditions there will be similar to those in space. There is no air or heat. Only in a spacesuit can you stay in this territory. Unfortunately, you won't be able to jump and fly because gravity still works. Besides, it's gravity that becomes the salvation of our planet. Both parts of the Earth won't fly away from each other because of the force of gravity. Instead, they will rotate and start to attract each other. In 100,000 years, both parts of the planet will reconnect once more, and the Earth will be completely renewed. Since the core is molten metal, it will return to a single heart, but it will take much longer to connect the solid rock of the halves. A scar forms along the entire fault. The scar will be overgrown with forests and flooded with oceans, but there will be strong earthquakes in some places near this scar. By this time, all living things have probably disappeared. On our planet, conditions are about the same as 4.5 billion years ago. Seas and oceans boil, lightning strikes everywhere, tectonic plates change their shape, and lava flows from volcanoes in a rapid stream. The Earth looks like a vast boiling pot, inside which life is gradually created. Because the Earth has decreased in size and the core hasn't changed much, the gravity will be different. On land, it will be more difficult for an ordinary person to walk. They will weigh much more. In such conditions, new, previously unknown life will be created. Today, the world's atmosphere and oceans are polluted, the population is increasing, and glaciers are melting. In the future, things could be much worse for our planet. In 1,000 years, when humanity has mastered space travel, we may decide to change our residence. We'll start looking for other Earth-like planets, and maybe we'll find something. However, nothing compares to our first home, and humanity decides to cure it. Perhaps we'll come up with the idea to divide the planet in half and live on one side. And after 100,000 years, we can come back to a new healthy home. What if you divide other planets? Since they don't have a magnetic field, they won't be as affected. For example, Venus and Mars have no seas, oceans, or lakes. Some scientists think they're entirely dried up because the magnetic field has disappeared there. This led to the complete destruction of the atmospheres of these planets. The solar wind blew across their surface with such force that it dried up all the liquid. The Earth's atmosphere reflects this wind, so thankfully, we're safe. There would be no significant cataclysms on other planets, except for earthquakes. Like Earth, the two parts of each world would simply rotate until they reconnect once more.